In this video, I will explain how the current behaves and how it relates to the inductor. So basically, the current is determined by the voltage over the inductor. So first we can look at how the voltage is determined. So we know that the voltage, VL, is equal to the voltage here minus the voltage here. So we have Vm minus the output voltage, which I just call VO. So Vm could either be high or zero. So either the input voltage or zero. So we can just write that up. So we have that it's either Vin or zero. While the output voltage is ideally constant. Let's say that it is constant, just to simplify. So we know that it's a constant between the input voltage and zero. So knowing all of this, we would know that VL could either be negative or positive. So, for example, when it's positive, it must be positive when Vm is equal to the input voltage. Because in that case, Vm would always be larger than the output voltage. Because we can see that the output voltage is between Vin and zero. So we can't be entirely Vin, but close to Vin. Or ideally, it could be actually equal to Vn. So the reason for why the output voltage cannot be equal to the input voltage is because we have some losses here. We, for example, have a little resistor here, which drops the voltage. Yeah, so this makes the inductor voltage be above zero. And in the case where the Vm is equal to zero, we know that we have a positive number here because it can never get zero. And then we have a zero here. So this would obviously be a negative number. So here VL is a negative. Now the reason why this is important is that we actually just have two different states of the inductor voltage. So in order to analyze the current, we need to look at the differential equation for the inductor itself. So we have that VL is equal to L multiplied with the derivative of the current. This you've probably seen before. So if we just solve for the current, we would get a constant multiplied with the integral of the voltage. So this means that, remember that this could either be positive or negative. So in the case where the voltage is positive, we know that the current is rising. So basically what I'm saying is that when this switch is on, we have that this voltage is equal to this voltage. So the voltage here is high, then the current inside the inductor will start to rise. And when this switch is off and this switch is on, we know that Vm becomes zero. So in that case, we would have a negative number on the inductor voltage. So therefore, we would get a falling current. So therefore, we know that the current would either rise or fall, depending on how we switch the switches. So here is a numerical example of this. So here you can see the inductor voltage is either positive or negative. So there are basically two phases. So in phase one, the current ramps up, and in phase two, the current ramps down. So that is why we get the ripple inside the buck converter. Okay, so now I want to show you how the current behaves when you change the output voltage. So in order to do that, we need to go to the simulator here. So you don't need to understand how the simulator works. You only need to understand that we have an input voltage, which is defined, and then we have an output voltage, or the reference voltage for the output. And then the switches here are controlled such that we get the output voltage that we want. And then we have the inductor and the capacitor load and the switching frequency of the switches. So here is the controller. So just know that it controls the output voltage, or it controls the switches so that we get the desired output voltage. So now if we run with this as it is, you can see that we get the same results as I showed you earlier. But what I want to do is I want to do a sweep. I want to sweep the reference voltage. so that we get different output voltages. And then we run it again. So now it looks a bit weird, but we need to add a slider. So here we define the reference voltage. So now it's 50 volts. And then if we increase it, we can, for example, have 75 volts. And then you can see that the current changes. But before I explain you how it changes, I think we should add the duty cycle as well. So we have the duty cycle there, so then we need another plot. So I'll just add it there. So here you have the duty cycle. So here it's 50%, as you can see there. And then I also want to add the output voltage. So the output voltage is up here, it's purple, while this is the duty cycle. So then we can try to sweep. You can see that when we change the reference current, you can see that we increase the duty cycle. So here it's a bit on top of each other. You can see that it's approximately 60% here, the duty cycle. And then you get a voltage which is 60, approximately 60. And what this does to the inductor voltage. So now if we look at VL and how it changes when we change the output voltage, we can see that VL is equal to VM minus the output voltage. So when we increase the output voltage as we did here, it is reasonable that the VL decreases. So you can see here that everything shifts down. So the top of VL is not 50 anymore as it was earlier. It's just below 50. And then the bottom is below minus 50. So the two states are both lower. And what this results in is that we get a lower slope when the current increases, and then a steeper slope when the current decreases. And that is simply because the voltage changes. But what this controller does automatically is it changes the duty cycle, which you can see here, to a value where we still are in steady state. Because if you don't change the duty cycle, you will see that the average current would start to increase or decrease. For example, if you still had a 50% duty cycle, but with a higher output voltage, you would see that on average, the current will decrease and become unstable. So that is why it's so important to control the current. You need to control the current so that it stays stable, because the output voltage could, for example, change, or maybe the input voltage could change and disturb the whole system. So it's important to keep the current stable. And now if we increase the voltage even more, you can see that we get an even steeper fall and a less steep increase. And then if the output voltage is very low, then we get the opposite effect. And here you can see that in this simulation, it didn't really reach steady state. So you can see that the current is still increasing. It hasn't reached the steady state yet. So that is basically how the current behaves. And like, if you're interested in this course, you can go to the link in the description. And if you're interested in this simulator, it is also in the description. And in my next video, I will show you how you can design the LC filter of the buck converter. So basically how you design the inductor and how you design the capacitor. So what I didn't tell you here is that the inductor value influences the rippling effect of the current. So the lower inductance, the higher ripple you will get. And the same thing for the capacitor. The lower capacitance you have, the higher the output ripple would be. So that is how it basically influences, and in my next video I will go more into detail on that.